Oh, and yeah, here's yet another presentation by me on Euler. Sorry if I sound quite tired. It's because this is the second time I'm doing this presentation, and that's actually bugging me. But anyway, let me get on with it. So this is Leonhard Euler, and I thought I'd jazz up my presentation with a little picture of him. He is responsible for so much mathematics. He really is. He is an incredible mathematician. Definitely in the top five, I guess, if there was a mathematicians league. You look at just what he did. He was a physicist, astronomer, geographer, logician, developed calculus, like graph theory, analytic number theory. There was just nothing he didn't have his, like, brain involved in, it would seem. Like incredibly clever mathematician. I believe he also wrote like a ridiculous amount of books. I don't know if it's in the Wikipedia here, but I know I've read it before somewhere that he's produced so many just crazy. Yeah, you might notice as well that eye. You can even see it in this photo. That eye is messed up because basically he had some kind of eyesight deterioration. But yeah, there we go. He's an interesting chap. I'd love to read more on him, actually. I've got a book on my shelf. Yeah, anyway, I'm waffling on. What we're going to try and prove is that e to the I theta, e to the I theta is cos theta plus I sine theta. You could argue that the whole of this chapter is really about the consequences of that result and what you can do with that result. The whole of the chapter. And this is a difficult chapter, but this is like a weird result. It's connecting trigonometry directly to the exponential function. That in itself is weird, because have we ever really discussed the exponential function, like as being heavily involved with trigonometry before? No, we've never expressed trig functions in terms of exponential functions. So it's a weird result, especially as it's got our old friend the complex number in there. So a lot of things to ponder here. Okay, let's try and prove it. Now, to prove it, I'm going to have to ask you to accept the following results. They are results which I've probably flashed up on the board before because I quite like them. They only work in radians. Those are factorials on the bottom, by the way. Um, you can always remember the cos one because it's the derivative of the sine one. It should be, cos is the derivative of sine. X differentiates to 1. X cubed over 3 factorial differentiates to x squared over 2 factorial, because 3 cancels with the times 3 on the bottom. Same here, this differentiates to x to the 4 over 4 factorial, and likewise x to the 6 over 6 factorial. Dot, 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 dot. Yeah, these do go on forever. I'm just showing you the first few terms of the pattern. You'll also need to accept this, that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Dot dot dot, that just goes on that pattern forever. Those are all examples of power series expansions, and you do prove them in chapter 2, so you will see these proved. I believe Miss Grant's going through that. I'll have to check. I can never remember what we arranged, but yeah, you'll see these results proved, do not worry, very soon, for those of you who need proof, and good for you if you do. Okay, let's just accept these as true. Accept as true, yeah, because I'm telling you they're true. But soon you'll prove them. Okay, now let's consider, basically, if I call these A, B, and C, in C, set x equal to I theta. Yeah, just so we know what e to the I theta is, and that just means replacing x with with I theta. So then we can see that e to the I theta is 1 plus I theta plus I theta all squared over 2 factorial plus I theta all cubed over 3 factorial plus, and I'm just going to do one or two more terms. I think maybe just one more term over 4 factorial. I actually know I'm going to do one more, plus I to the theta to the 5 over 5 factorial. Yeah. So far, so good. Nothing too interesting going on. I want to point out though, I to the power of 1, that's I. I squared, that's minus 1. I cubed. Now, I wonder if you've seen this before. Sorry. I wonder if you've seen I cubed before. Well, that's just I times the last result, so it's minus I. And I to the power of 4, well, that's minus I times I, which is minus I squared, but I squared is minus 1, so that's 1. And it goes round in a lovely circle like that. I minus 1 minus I1. I minus 1 minus I1. So on and so forth. The next one, I to the power of 5, is simply going to be I, because I'm timesing the last result by I. Let me write it down, actually, just so you can see. The pattern is going to repeat. Okay, that helps me simplify this into the following. 1 plus I theta. And then when I square the I, I'm going to get minus theta squared over 2 factorial, because I squared is minus 1. And when I cube the I get minus I theta cubed over 3 factorial. And when I do I to the power of 4, I get 1. So this is plus theta to the power of 4 over 4 factorial. And then here I'm going to get plus I theta to the power of 5 over 5 factorial. Okay, so notice the pattern goes plus plus, well, plus plus minus minus plus plus, and it will be minus minus coming next. So it will be because I to the power of 6 is going to be times up by I, you get I squared minus 1, so I'm going to have minus, I'll even put it on the end, minus theta to the power of 6 over 6 factorial dot 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 dot. Yeah. Okay, so I've got lots of terms there. Now consider basically cos theta plus I sine theta. Cos theta plus I sine theta. Well, cos theta is just the one for cos x, and then sine, but multiplied through by I. So what we're going to have is this: cos theta plus I sine theta. Well, that's going to be theta. Oh, sorry, 1. Let me do the cos theta terms first. 1 minus theta squared over 2 factorial plus theta to the power of 4 over 4 factorial minus theta to the power of 6 over 6 factorial. That would be right, dot, dot, dot. And then it's plus I times sine theta. Now, sine x is simply x minus x cubed. All I've got to do is times all those terms by I. Yeah? So I'm going to have, oh, and remember, I'm using sine theta. So I'm going to have I theta minus I theta cubed over 3 factorial plus I theta to the power of 5 over 5 factorial. And I'll just leave it there and put dot, dot, dot. And now look at this. This is the line above. It's the I theta line. And because of that lovely pattern we've got with the powers on I, you can just see that that pattern's going to continue generating the entire e to the I theta function. Yeah? Can you see? Maybe if I write it down in the same order now. Those two added together make that bit. And then we get minus theta squared over 2 factorial minus I theta cubed over 3 factorial. And then we get the next two terms, theta to the power 4 plus I theta to the power 5, theta to the power 4 over 4, plus I theta to the power 5 over 5. Do you see we get exactly the same result? It's a remarkable result. It really is. And it proves that e to the I pi plus 1 is 0. Yeah? And you can prove it just by plugging in theta as pi. Yeah, this is your result. If you let theta equal pi, then you're going to get cos of pi, that's minus 1, sine of pi, that's 0, and then e to the I pi. And then add it over, e to the I pi plus 1 is 0. It's supposed to be the most beautiful result in maths, that, the prettiest result in maths. Okay, now why do we do this? Why do we do this? Well, we do it, and I'm really nervous actually about continuing the video, because when I continue the video, and this is what happened before, it crashes, and then I get really, really, really irritated. Okay, mostly through the exercise. If you read example 6, to be honest, you'll be absolutely fine with the exercise. I'm certain. It should be absolutely fine. Like sorry, example 6. What am I talking about? I'm on the wrong page. Example 2, 3, and 4. Right, they're all fine. Example 5's tougher, but examples 1, 2, 3, and 4 should be fine for doing the exercise. But essentially, what it does, this formula, is it helps us link cos theta plus sine theta times r, which I hope you remember is the modulus argument form for writing a complex number. It's basically a way of saying the complex number is this angle above, turning from the positive x-axis, and r is the length, the distance, in other words, from the origin. Well, we can write it instead much quicker. I'm sure you'll like this for the lazier like myself amongst you. You can just write it as re to the I theta. That makes it so quick to write down the modulus argument form. And it's not just useful for being speedy in writing it down. It also helps you do all kinds of problems. Like there's some really cunning tricks you can do with e to the I theta. It's genuinely really handy. So in that first exercise, you're literally just converting from here to here, and really all you've got to be careful about. Bear in mind you can use this trick. Cos of minus theta is cos of theta, and also minus sine of minus theta. Well, that's sine theta. That just says that cos is an even function as sine is an odd function. I don't suppose you've read those definitions before, but that's a really handy trick, certainly sometimes in some of the questions in the exercise. Exercise 1a, question 1h and 1i, I think will be very handy because you want that to be plus I. So yeah, have a look at the questions in the exercise. Do let me know if you're stuck in any of this, and come and speak to me on the Maths Help Desk if you are.